A nuclear power plant is a thermal power station in which the heat source is a nuclear reactor. As is typical in all conventional thermal power stations, the heat is used to generate steam, which drives a steam turbine connected to an electric generator which produces electricity. As of the 23rd of April 2014, update, the IAEA report there are 435 nuclear power reactors in operation operating in 31 countries. Nuclear power plants are usually considered to be baseload stations, since fuel is a small part of the cost of production. History. For more history, see nuclear reactor, nuclear power and nuclear fission. Electricity was generated by a nuclear reactor for the first time ever on September 3, 1948 at the X-10 graphite reactor in Oak Ridge, Tennessee in the United States, and was the first nuclear power plant to power a light bulb. The second, larger experiment occurred on December 20, 1951 at the EBRI experimental station near Arco, Idaho in the United States. On June 27, 1954, the world's first nuclear power plant to generate electricity for a power grid started operations at the Soviet city of Obninsk. The world's first full-scale power station, called a hall in England, opened on October 17, 1956. Systems. This section has recently been translated from the German Wikipedia. The conversion to electrical energy takes place indirectly, as in conventional thermal power plants. The fission in a nuclear reactor heats the reactor coolant. The coolant may be water or gas or even liquid metal depending on the type of reactor. The reactor coolant then goes to a steam generator and heats water to produce steam. The pressurized steam is then usually fed to a multi-stage steam turbine. After the steam turbine has expanded and partially condensed the steam, the remaining vapor is condensed in a condenser. The condenser is a heat exchanger which is connected to a secondary side such as a river or a cooling tower. The water is then pumped back into the steam generator and the cycle begins again. The water-steam cycle corresponds to the Rankine cycle. Nuclear reactors. A nuclear reactor is a device to initiate and control a sustained nuclear chain reaction. The most common use of nuclear reactors is for the generation of electric energy and for the propulsion of ships. Nuclear reactors usually rely on uranium to fuel the chain reaction. Uranium is a very heavy metal that is abundant on Earth and is found in seawater as well as most rocks. Naturally occurring uranium is found in two different isotopes. Uranium-238, accounting for 99.3% and uranium-235 accounting for about 0.7%. Isotopes are atoms of the same element with a different number of neutrons. Thus, U-238 has 146 neutrons and U-235 has 143 neutrons. Different isotopes have different behaviors. For instance, U-235 is fissile, which means that it is easily split and gives off a lot of energy, making it ideal for nuclear energy. On the other hand, U-238 does not have that property despite it being the same element. Different isotopes also have different half-lives. A half-life is the amount of time it takes for half of a sample of a radioactive element to decay. U-238 has a longer half-life than U-235, so it takes longer to decay over time. This also means that U-238 is less radioactive than U-235. The nuclear reactor is the heart of the plant. In its central part, the reactor core's heat is generated by controlled nuclear fission. With this heat, a coolant is heated as it is pumped through the reactor and thereby removes the energy from the reactor. Heat from nuclear fission is used to raise steam, which runs through turbines, which in turn powers either ships' propellers or electrical generators. Since nuclear fission creates radioactivity, the reactor core is surrounded by a protective shield. This containment absorbs radiation and prevents radioactive material from being released into the environment. In addition, many reactors are equipped with a dome of concrete to protect the reactor against both internal casualties and external impacts. Steam turbine. The purpose of the steam turbine is to convert the heat contained in steam into mechanical energy. The engine house with the steam turbine is usually structurally separated from the main reactor building. It is so aligned to prevent debris from the destruction of a turbine in operation from flying towards the reactor. In the case of a pressurized water reactor, the steam turbine is separated from the nuclear system to detect a leak in the steam generator and thus the passage of radioactive water at an early stage. An activity meter is mounted to track the outlet steam of the steam generator. In contrast, boiling water reactors pass radioactive water through the steam turbine, so the turbine is kept as part of the control area of the nuclear power plant. Generator. The generator converts kinetic energy supplied by the turbine into electrical energy. Low-pole AC synchronous generators of high-rated power are used. Cooling system. A cooling system removes heat from the reactor core and transports it to another area of the plant, where the thermal energy can be harnessed to produce electricity or to do other useful work. Typically, the hot coolant is used as a heat source for a boiler, and the pressurized steam from that drives one or more steam turbine-driven electrical generators. Safety valves. In the event of an emergency, safety valves can be used to prevent pipes from bursting or the reactor from exploding. The valves are designed so that they can derive all of the supplied flow rates with little increase in pressure. In the case of the BWR, the steam is directed into the suppression chamber and condenses there. The chambers on a heat exchanger are connected to the intermediate cooling circuit. Feed water pump. The water level in the steam generator and nuclear reactor is controlled using the feed water system. The feed water pump has the task of taking the water from the condensate system, increasing the pressure and forcing it into either the steam generators or directly into the reactor. Emergency power supply. Most nuclear plants require two distinct sources of off-site power feeding station service transformers that are sufficiently separated in the plant switchyard and can receive power from multiple transmission lines. In addition, in some nuclear plants the turbine generator can power the plant's house loads while the plant is online via station service transformers, which tap power from the generator output bus bars before they reach the step-up transformer. Even with the redundancy of two power sources, total loss of off-site power is still possible. Nuclear power plants are equipped with emergency power workers in a nuclear power plant. Nuclear engineers, reactor operators, health physicists, emergency response team personnel, Nuclear Regulatory Commission resident inspectors. In the United States and Canada, workers except for management, professional and security personnel are likely to be members of either the International Brotherhood of Electrical Workers or the Utility Workers Union of America, or one of the various trades and labor unions representing machinist, laborers, boilermakers, millwrights, iron workers, etc. Economics. The economics of new nuclear power plants is a controversial subject, and multi-billion-dollar investments ride on the choice of an energy source. Nuclear power plants typically have high capital costs, but low direct fuel costs, with the cost of fuel extraction, processing, use and spent fuel storage internalized costs. Therefore, comparison with other power generation methods is strongly dependent on assumptions about construction timescales and capital financing for nuclear plants. Cost estimates take into account plant decommissioning and nuclear waste storage or recycling costs in the United States due to the Price-Anderson Act, with the prospect that all spent nuclear fuel, nuclear waste, could potentially be recycled by using future reactors, generation IV reactors. that are being designed to completely close the nuclear fuel cycle. On the other hand, construction, or capital cost aside, measures to mitigate global warming such as a carbon tax or carbon emissions trading, increasingly favor the economics of nuclear power. Further efficiencies are hoped to be achieved through more advanced reactor designs. Generation 3 reactors promise to be at least 17% more fuel efficient, and have lower capital costs, while futuristic Generation IV reactors promise 10,000 to 30,000% greater fuel efficiency and the elimination of nuclear waste. In Eastern Europe, a number of long-established projects are struggling to find finance, notably Berlin in Bulgaria and the additional reactors at Avda in Romania, and some potential backers have pulled out. Where cheap gas is available and its future supply relatively secure, this also poses a major problem for nuclear projects. Analysis of the economics of nuclear power must take into account who bears the risks of future uncertainties. To date, all operating nuclear power plants were developed by state-owned or regulated utility monopolies where many of the risks associated with construction costs, operating performance, fuel price, and other factors were borne by consumers rather than suppliers. Many countries have now liberalized the electricity market where these risks and the risk of cheaper competitors emerging before capital costs are recovered, are borne by plant suppliers and operators rather than consumers, which leads to a significantly different evaluation of the economics of new nuclear power plants. Following the 2011 Fukushima I nuclear accidents, costs are likely to go up for currently operating and new nuclear power plants, due to increased requirements for on-site spent fuel management and elevated design basis threats. However, many designs, such as the currently under construction AP1000, use passive nuclear safety cooling systems, unlike those of Fukushima I which required active cooling systems. This largely eliminates the necessity to spend more on redundant backup safety equipment.